Okay, composite functions. Guys, fasten your seatbelts because this is a biggie, okay, and it's very badly misunderstood, so hopefully you will understand it after I've finished with this video, okay? What is a composite function? Well, a composite function is a function of a function. Well, that sounds like it's clear as mud, doesn't it? Let's unpack that a little bit. If we had f of x and g of x, then the composite functions possible are f of not x but g of x, which is affectionately in my language known as fog, and you could also have g of f of x, which I call affectionately goff, although there's not much affection anywhere for these things, I can assure you. There are compatibility issues to resolve before it is determined whether fog or goff exist or are defined, and this is the sticking point with understanding these composite functions, the compatibility issues, which I'll go into in great detail for you. If any compatibility conflicts are not addressed, then the composite function is not, repeat, not defined. Composite functions can be best thought of as the result of a two-stage mathematical assembly line, quote unquote, or a factory type process. Now, here is our factory. This is stage 1 and this is stage 2. In this case, we're doing f of g of x. Now, think of it this way. You've got g of x. You've got all the little x's coming in here, which its implied domain, coming in here, and there's the g function happening, and what comes out the other end is the product of that little factory, or that part of the factory, which is g of x, okay? But this is an assembly line process, so this is like a belt conveyor, okay? All the little x's go in through the belt into the machine, they get changed into g of x's. So what happens here is the factory continues, and these g of x's then go into the second part of the factory, which is the f process, and they get transformed through the f process into f of what went in, which is the g of x. So you get f of g of x coming out the end, okay? Now that is the process in simplicity, okay? X is the input to the g process, which is the domain, and g of x is the output of the first stage of g, which is the range of g. You get that, don't you? In the second stage, okay, the output of g here becomes the input into the f stage, okay? It is the domain of this second stage, because remember, think of this like a conveyor belt. What comes out of here has to go straight into there as its input, okay? So in the second stage, the output of g feeds into f as its input or domain, okay? Are you getting this? That's the concept. I just want you to get the concept. Thus, the output of the second stage f is f of g of x, not f of x, because x didn't go in there. G of x went in there, okay? That's what it's all about. If the output values from stage 1, which are g of x, are not compatible with the acceptable input values into stage 2, which in this case is f of x, then f of g of x is not, repeat, not defined. That is the cruncher, okay? In mathematical terms, ladies and gentlemen, we say that the range of g of x, which is this, okay, has to be wholly contained within the domain of f, or if that's not the case, then f of g of x is not defined or is undefined, okay? That's it in a nutshell. That is the compatibility thing which we have to deal with in the middle. This range of g has to be wholly contained within the implied domain of f. Otherwise, all bets are off. It's no good. Okay? Okay, let's keep going. Now, if the range of g is not wholly contained within the domain of f, then the input or the domain of g can be restricted to those values, that's these little beasties here, can be restricted to those values which produce an output or range of g which is compatible with the input or domain of stage 2, which in this case is F. You get that? After any incompatibilities of the interface between stage 1, which in this case is G, and stage 2, which in this case is F, have been resolved, then and only then, ladies and gentlemen, the domain of the composite function is the domain of the left-hand side here. Okay, of the overall composite function is the domain of the left-hand side, and the range of the composite function is what comes out the right-hand end. Okay, the range of F with the input that's going into it from here. That's pretty important. Now, all that seems like a lot of theoretical hot air, but it's really important that you get the concept, because if you get the concept, you'll understand how to do these things. So I've put a big cloud around this whole little factory process. Assuming that there's compatibility in here, then the domain of the composite function is this, what's going into this end, and the range of the composite function is what's coming out of that end. And you can sort of basically just don't worry about what's going in there. Once you've got all that resolved, then you can just think of it as a little black box cloud-like mechanism, because you've got the inside of it sorted out, and that's the domain and that's the range. Okay, good. So when we're determining fog or GOF, that is f of g of x or g of f of x composite functions, we firstly check for compatibility at the interface to check that the composite function is defined. Okay, that's the very first thing we do, always. Domain range tables can be used to check for compatibility. That's one way that you can do it. Okay, I'll show you one in a minute. E.g. for f of g of x, g is the stage 1 function and f is the stage 2. Okay, you can easily understand that from the way I've described the process up here. Yes? Now, so therefore what we're saying is that the range of g must be wholly contained within the domain of f in order for fog or f of g of x to be defined. Okay, that's what we're saying. For example, if g of x was x and f of x was x squared, this would be pretty easy because neither of them are fussy. Usually you get a problem where stage 2 is a fussy function. That's where you usually start to come unstuck by having to sort out the incompatibility issues in the middle. But we're going with this. G of x equals x, that's stage 1, f of x equals x squared. Okay. Now here's a domain range table. Have a look at this. This up here we have the domain in this column, the range in that column. We have stage 1 in row 1 and stage 2 in row 2. Stage 1 is g of x. There's its implied domain. If g of x equaled x, well, of course, that would be all real numbers. And, of course, we know that the range would be all real numbers as well, corresponding to that particular domain. For stage 2, which is f of x on its own, without any influence from stage 1, its domain would be f of x equals x squared. Well, that would be all real numbers, yeah? And the output or the range of f of x all by itself, without any influence from g of x, would be from 0, including 0, up to infinity. Okay? Now, looking at the middle, okay, looking at how the range of the first one impacts the domain of the second one, we put a little loop around there, and we can see, ladies and gentlemen, that the range of G, which is R, is wholly contained within the domain of F, which is also R. They coincide, and you can say therefore that this is wholly contained within that. In fact, it coincides exactly with it, but it's the same thing to all intents and purposes. All right. So therefore, f of g of x does exist. What a happy ending to our little story. Okay.